All right, okay. So observational constraints on black hole seed formation and early growth. I think we're now in the era where we can actually make statements about that. And I sort of want to walk you a little bit about some recent observational work we've done and perhaps sort of raise new questions, because I think this whole seed formation question is both one of the most interesting ones, but also I think we're at the very beginning of that road. So technology. This is the theory slide, which Amy already showed this morning, so I don't really need to talk about it. But so theorists, including people in the room, have sort of given us some options about what might be happening. And so the three sort of generic categories here from a review paper by Marta is we have the direct collapse model, where gas basically just collapses all the way down under special conditions in the early universe. We have the remnants of population 3 stars, where first generation of stars collapses all the way down to a massive, still very massive black hole, but much less massive than in the other case. Or you could have fragmenting gas forming a dense star cluster, which then collapses all the way down to a black hole seed. So these are sort of the theory options. And I won't say much more about that other than this is sort of an initial guideline to what we might be looking for. So first, before I go in the completely other direction, the universe makes massive black holes, 10 to 9 solar mass black holes, less than 1 billion years after the Big Bang. And this is a problem because the characteristic growth time for a black hole, the saltpeter time, is about 45, 50 million years. And so the e-folding time is long enough that this age, 750 million years of the Big Bang, if you assume you don't start right after the Big Bang, but wait for the first stars to form, this is tight and probably not feasible if you stay within the Eddington limit. And so people have said, well, we need really massive seeds. So the thing that starts accreting and growing as fast as it can is already quite massive. Or super Eddington accretion. But so unless that's dim, if that's bright, I'll get back to that. Maybe we should have seen it. This is the Mortlock et al. UKIDS Quasar at Redshift 7.1 or whatever it is. And this is the composite spectrum. What I really love about this plot, actually, as a total aside, the red line here, this is not a fit. This is just a composite spectrum of quasars from Sloan. So a Redshift 7 quasar is, as far as the spectrum is concerned, identical to Redshift 1 or 2 quasar. So it doesn't care about what epoch of the universe it lives in. And I think that's a fascinating fact about quasars and the early universe.
Could you review the argument for this being a billion star mass black hole?
Could you review the argument, the observational argument for this being a billion star mass black hole?
I believe these are virial masses.
It's the magnesium 2 line width mostly, so there's also Eddington arguments. Simple Eddington means it's 10 to the 9, and then they have the empirically calibrated line width.
This is incredibly bright than if it was.
Simple Eddington sort of implies that you're assuming it's Eddington. Maybe it's 10 times. Yeah, it's a circular argument.
Yeah, but then you go back to the line width.
Well, it's not Eddington, but it's more massive.
Yeah.
So I want to make a comment.
If it's highly super Eddington.
Oh, highly super. Yeah. But then the statement is, why would the optical spectrum highly super Eddington object be the same?
Well, okay, so this is an almost philosophical point, but I think it's worth making here. We recognize it because we're looking for something that has the spectrum. So I don't think it's a surprise that it fits.
No, but it's not.
There can be all sorts of other weirdness out there that are quasars, but we don't know how to recognize.
Sure, but so my only point here is it's not that it fits so remarkably well. I think that is interesting. And I completely agree with your point. We actually don't know necessarily what to look for. And again, I'll get to that. The question of what is the observational signature of the first phases of black hole growth is, we don't really know. And I'll get to why this is actually tricky to figure out.
I could actually comment that even at Redshift 5, there are some quasars that don't even look like that.
Yeah. Very strange lines.
And Marian, isn't that right that this magnesium line-based masses are to be taken with care, especially at high redshift when there could be lots of altitude.
Well, I think it depends on how well you can actually decompose. You see that magnesium-2 is sitting in this big lump of iron, and that's the big question. But there are different lines you can look at, and they all kind of seem to point towards, I would say within a factor of 5 to 6 or even 10 is probably.
Could you go back, because you just said a magic word, iron.
Yeah.
Iron in a redshift of 7 when the universe is 750 million years old.
So what?
Not a problem.
Yeah, what's the problem with that?
Massive stars.
No, type 1As with short time delays.
Well, you see it, right?
Oh, yeah, that's...
And it's not iron spread across the whole galaxy. All you need is iron right in the very center. Like, do you get enough iron out of a single type 1A supernova to explain the spectrum? Probably yes. Or a handful.
I guess this would be a question for the people who actually look at these supernovae.
You need just a bunch of systems with single degenerate type 1As to make a lot of iron.
The big question is actually how much iron do you really need to produce the iron spectrum?
Yeah.
We don't know that, and you may not need very much because it's an extremely efficient form.
Yeah.
Yeah.
Is there any way to estimate what the metallicity of this gas is?
Yes, Simcoe has.
Yeah, that would be similar to line ratio stuff. It's not as accurate as you can do for absorption studies, but you can still get within a factor of, I don't know, what do you think, Mike?
Yeah, from the broad emission lines,
Yeah.
you can get some estimates of the metallicity. I don't know. I would say a factor of a few, just guessing.
So
in this
Plus
particular
it's the
source,
gas that's right there, not the gas.
okay, so if in this particular source they also see the 158 micron line of carbon,
I'm going to
which gives you the ISM metallicity and not the AGN metallicity.
Yes.
And it's fairly high metallicity. You see the carbon line, which is very interesting because just outside of it in the absorption in the intergalactic medium, it's very low metallicity. So it's highly inhomogeneous medium. It's really cool.
I have this stick, so I'm not just going to talk. I'm going to moderate, and Kelly wants to say something.
I'm so sorry. We should let you get on with your talk.
No. This is great because
I wanted to throw one small comment out, just as one of the many people who grow black holes, and that is that folks always worry about the 10 to the 9 solar mass black holes at high redshift, and with this straw man argument of saltpeter time, or oh my goodness, we have to worry about super Eddington accretion. And I think people forget that if you have just a few mergers of the black holes, and then you E-fold on that, you're fine. So it is not that big of a problem to grow very big black holes by redshift 6. Free-range black holes. Sorry, we were talking over lunch about free-range black holes, and we thought it was very hilarious.
Yeah. Free-range black hole.
Yeah, so it was a joke. Okay. But anyway, the point is that this sort of argument is a bit.
Well, I'm trying to transition from the slide to make the following point: is that I don't care about the Redshift 7 quasar because it's an enormous statistical outlier. We have one in how many thousands of square degrees? Okay, I want to know where normal black holes come from and how do they have their early growth and how do they affect their host galaxies ultimately. Where do the kinds of black holes come from that end up at the center of the Milky Way and local massive galaxies? So it's not Redshift 7 quasars, which are enormous outliers because that's just not where they come from. So the image here in the background is the 4 megasecond Chandra deep field. And so this is a pencil beam survey now. And so we're looking at a tiny area on the sky. And because of cosmology, the volume at redshift 6+ that we're looking at is much, much smaller. And so in theory, in this volume at high redshift covered by this beautiful, beautiful deep Xray image from Chandra, we're seeing more normal galaxies grow up. So we see Lyman break galaxies in that field in the first 200 million years of the universe, and we see them grow up. And these are small dwarf galaxies, actually sometimes perhaps even smaller than Hen-Ice 210, but they're the things that grow up by redshift 0 to be massive galaxies. So we've been stacking Lyman break galaxies in redshift 6 to 8 in Chandra, and this is really, really good, really easy to do because Chandra has such a low background that by stacking, you don't go as square root of t in terms of signal noise. You almost go as t. And so at the Redshift 6 sample, this is now large enough, compiling Bowens et al., Finkelstein et al., various people's compilations now from candles. You have an effective exposure time with Chandra on the Redshift 6 Lyman break galaxies, something like 20 years. So this is a really, really deep observation. And what we find is interesting. We don't see anything. We get upper limits in X-ray luminosity. And to remind you, at redshift 6 to 8, you moved by a factor of enough that Chandra is a hard X-ray telescope. So to 0th order, but I'll get back to that later, to 0th order, obscuration is not an issue here. So we should really have a clear view on the average accretion properties of Lyman break galaxies. And we get these upper limits that are at redshift 6, we're down to about 3 times 10 to the 41 ergs per second on average, all the way to redshift 8, where we just have fewer sources, we're about 1.5 at 10 to the 42 in the soft band, and then slightly higher in the hard band. And using a sort of inverse kind of Zoltan argument type reasoning, you can turn this upper limit in terms of the luminosity into a volume density in accreted black hole mass that we can see in the universe at that redshift. And these limits now are at the point where it gets interesting. So let me illustrate what I mean by interesting limits. So what I'm plotting here is the accreted black hole mass density as a function of redshift. We have a fairly good redshift 0 point, and we have a whole bunch of points from different X-ray luminosity functions and people's fits to them, and you can project them backwards. So the black one is one luminosity function projected all the way down to redshift 10. And then what you can see here are our points. These are our upper limits. This is what we can say is not there. And over plotting on that, we could take models, for example, Mater Voluntaries, models for different kinds of seeds and different kinds of, do you have self-regulation or not, by which, from what I understand, is basically meant is, do you tie the black hole mass? Do you force it to essentially grow in tandem with the galaxy? Do you have something like M sigma right from the start? And what you can see is that we're now in the regime where, whether you believe in pop 3 stars or direct collapse, as long as you have some kind of what the theorists now call self-regulation going on, it's tough. At redshift 6, we're a factor of a few off of what we should be able to see. So, to put another way, to go back to those limits, if the average Lyman break galaxy at redshift 6 had a 10 to the 6 solar mass black hole, so like Henneis 210, and had a 1% Eddington ratio on average, we should have detected that, and we don't. This is what I mean by these constraints are starting to be interesting. So we see nothing on average, and we see no, I should have mentioned that, we see no individual detection. So no Lyman break galaxy candidate that's been published by the galaxy evolution people has an X-ray counterpart. That's actually also an interesting statement, and I'll get back to that later. So this is where I go to what the hell is going on here. And we don't have a good explanation for why we see nothing, other than that it leads down interesting paths. And so I'm going to list a couple, and I'm sure people are going to have comments, but I try and get through the list before we entirely stall. So the simplest explanation is, well, Lyman break galaxies redshift 6 to 8 have a low occupation fraction. They just don't have black holes in them, which might imply that seed formation in normal galaxies at that redshift is inefficient. They just don't have black holes yet. They're not growing yet, which is why we don't pick up a signal.
Did you say the mass limit? Again, you said 1% efficiency, 10 to the 6
solar masses.
Is that what you're talking about? That's pretty low.
Yeah, it is low because you can stack so deep, and we have so many Lyman break galaxies now.
6. So if it followed the M sigma relation, then the halo, the bulge has the few 10 to the 8. These are low mass galaxies.
I mean, the masses are uncertain. They range from 10 to the 7 to 10 to the 9 in general. Well, we don't have masses for these things. We have 2 or 3 photometric points at the extreme UV, and we fit complex models with or without emission lines to them. Like, who knows what the masses of these things really are?
Should be more than 10 to the 7?
At that redshift? And people get different kinds of fits.
I thought they were 10 to the 9.
Yeah, people report a wide range because, I mean, you're fitting 2 or 3 points and a whole bunch of upper limits. And there's a lot you can fit through those points. Okay. Another option. Lyman break galaxies have black holes, maybe even massive black holes in them, but for some reason they're not growing. So if they don't accrete, they don't emit X-rays, we don't get anything in the stack. So if they're not growing, immediately to me raises the question, why not? these galaxies have very high specific star formation rates, and that means they should be gas-rich, which means there's certainly enough fuel to feed the black hole. And so you could always say in a specific case, well, okay, you're not accreting right now because you're not feeding, but on average, it seems a little odd that we're not catching any of them accreting. So, okay, maybe they don't contain black holes that are not growing by accretion, but that seems a little odd given everything we know about these galaxies. But, for completeness sake, we have to list it. Okay, Lyman break galaxies, the black holes in Lyman break galaxies are growing, they're accreting, but they're radiatively inefficient, or they're heavily obscured, or they grow by mergers. They grow by some completely other process. So I put down, okay, question mark, question mark, question mark, because if that's the case, how do we make progress? It's not clear.
Well, it's even worse, because if they're growing by mergers, then there's no radiative signature of merger.
Yes. If they are basically, if the dominant mass growth mechanism at that redshift in normal galaxies is black hole mergers, how do we ever study that? And I think
hoping that you'd have a radiative signature.
Right. And we need ultra with umlaut JWST to do that? Uber JWST.
They might have a radiative signature, but we don't know what it is, which is just as bad.
Yeah, just looking for photons.
Yeah.
So probably at 40th magnitude, maybe? It's going to be tough. Okay. And the fourth one, I think this was an interesting perspective, and I had a student really look into this, and she just finished her thesis on this. The black holes in these galaxies that grow in Lyman break galaxies elude to the classical Lyman break selection. And there was a bunch of things that we thought of immediately of why this might be. And it could just be that they just look odd and they don't make it into the classic Lyman break color selection cuts that people like to make. One thing we found out along the way is that several of the Lyman break galaxy teams, for I think understandable reasons, have a stellarity cut on their Lyman break galaxy selection. So they threw out things that were point sources, or point source dominated, because they didn't want ultra cool stars in the galaxy. But of course, if it's an unobscured AGN, that's exactly what it looks like. So that was
a morphological cut.
Yes. Well, I mean, it's a stellarity cut. Is it how much? Is it a point source or not? So if they threw out the point source, maybe they just threw out all the Lyman break galaxies with growing black holes, or the host galaxies during the phase where the black hole grows is dusty, so you just need a little bit of dust, and those faint, tiny little Lyman break galaxies drop out even out of the ultra deep field. Again, if that's the case, what do? We have to wait at least till JWST to catch them. Yep. Okay.
On your last point, just to understand the possible severity of this issue, if there was a growing AGN, how luminous would it be compared to the host galaxy? In other words, would it fill in the Lyman break? And so there would be no Lyman break because light from the AGN.
Would you have the absorption, intergalactic absorption?
Yeah, the Lyman break is
huge to the
IGN.
Yeah.
Okay.
So, and I'll get exactly to that. So we can come back to this list, because I first want to address this point of, well, maybe we deselected by accident or somehow by design all the growing black holes. So again, Chandra deep field, 4 megasecond deep field. And I had a student, Anna Weigel, do a master thesis on taking every Xray source in this field detected in the catalog and evaluate it based on its HST plus Spitzer observed photometry to test using just straight Lyman break dropout criteria and color cuts, and then later photometric redshifts, whether there were any sources in this field that could plausibly be X-ray sources, so growing black holes, at redshift 6+. And so we put a lot of work in this. We tried to be really careful. We examined each candidate not just automatically, but also by eye. Turns out some cases can be really tricky. So I'm just showing an example here. The X-ray hard and soft cutouts, and then the goods and candles postage stamps. So this is a nice B dropout galaxy. It's a AGN at low redshift. Here's another object that's actually quite bright in the X-rays, and it doesn't appear to be in any of the optical images, but it's bright in the near-infrared images. And maybe there's a residual here, yes or no. And this is where it gets really tricky when you evaluate: is this thing really a dropout or not? Is this actually a dusty galaxy at redshift 2 that hosts a moderate luminosity AGN, or is it at very high redshift? And again, these images yield clues. This thing is really bright in the near-infrared, and it's actually also quite extended. So just based on that, it's probably not a high redshift galaxy with an AGN in it. So we did a lot of work on these sources, and we ended up with a bunch of candidates, and we did detailed photo-Z analyses. And what we concluded is that none of the X-ray sources that had optical near-infrared counterparts had a good case to be made to be at redshift 6+. We didn't find any plausible candidate. She was a little disappointed at the end, but this is how science moves forward. In the end, what happens is all the apparent dropout galaxies or red galaxies, they either have a very nice photo-Z around redshift 2, or what you often end up with is you have a peak about redshift 2 and a redshift 6. And unless the high redshift minimum is a lot lower than the redshift 2 one, you forget it. The likelihood of a galaxy being a redshift 2 versus redshift 6 is vastly higher. And it turns out most of these X-ray sources are basically red dusty galaxies with moderate luminosity AGN. They're your main contaminant. Now, what remains is I think there are 7+ sources in the combined, 7 sources in the combined 4 megasecond deep plus candles plus goods footprint that have no optical near-infrared counterpart. Now, we can say nothing about those sources because they have no counterpart other than they have a few X-ray counts. So these would remain your possible, the last refuge of growing black holes at very high redshift. And of course, if you have no counterpart in multi-orbit HST exposures, I think we're very far off trying to figure out what they are. And if I had to bet, just on what we learned here, they're probably just going to be redshift 2 galaxies with low luminosity AGN. So how do we make progress on this? So we really want to move forward by going wide rather than deep. So we have 2.7 megaseconds to now cover the whole cosmos field with Chandra at several hundred kiloseconds depth. And the reason we want to do that is the volume that you get at redshift 6+ in the central region of first the ultra-deep field where we have all the beautiful Lyman break galaxies and just the general 4 megasecond field, it's actually not a lot of volume. And so if you go to a larger area, even if you're shallower, the odds that the volume you probe becomes larger. And there it gets interesting, because if you take predictions from, say, Marta Volonteri's models, depending on what your starting seed mass is and what you assume about the further evolution, you would expect 0, 1, 2, maybe a few sources in an area that large. And so if we start finding sources in a much larger survey, we're starting to get a handle about at least extreme objects, which are still not nearly as extreme as the Redshift 7 quasar, but are sort of the tip of the iceberg of the normal galaxy black hole population. So let me completely switch gears, and we can come back to the laundry list later. Okay, we don't have any good indication that black hole seeds form and grow in high redshift galaxies. So what if they just don't grow in the very high redshift universe? What if the universe keeps populating galaxies with new black holes even at low redshift? So I'm going to show you one object that I've found by chance, which I think puts an interesting new spin on this idea. So this is a nice HST WIF3 IR infrared image. And as part of various surveys, people have now used the GRISM on WIF3 to basically take spectra of everything, and it's a mess, and you spend a lot of time reducing the data. But occasionally you find interesting things, like this X-ray source in the Goods North field up here. I'm going to zoom in on it. It looks like this. So here's the image, and here's the dispersed image. And so you see the emission lines here, and they're displaced basically because they're displaced in the image. So you extract the spectra. Well, you look at the HST image. It appears to be a sort of a clumpy, multi-clump galaxy that's actually common at high redshift. Turns out this one is about at redshift 1.3. It's a bit of a Rorschach test, what do you believe about galaxy evolution. Some people see a 3 or 4 way merger here. Other people see a classic clumpy disk galaxy here. Could be either, but both are interesting options. Now, what makes this galaxy so interesting is that clumps A, B, and D, the bright ones, contain AGN, contain growing black holes. And we know this from huge O3 to H beta ratio. The whole thing, the whole object is a Chandra source. It's an X-ray source. But it's too far off the aim point to be able to resolve where the X-rays are coming from. And we can more or less rule out an ultra-low metallicity starburst that would also give you a huge O3 to H beta ratio based on the fact that this thing is massive. And if you apply the fundamental metallicity relations, so the relationship between star formation rate and stellar mass and gas phase metallicity, we can basically completely rule out the idea that this is a low metallicity starburst in these clumps. So we have 10 to the 6 to 10 to the 7-ish solar mass black holes growing near or at Eddington inside the clumps of this galaxy.
Which ones do you think have AGNs?
A, B, and D. C is too faint and too, you disperse sort of in this direction, so B is almost completely covered by C.
Do you have them on the BPT diagram? Sorry, the O3.
You can't put them on BPT diagrams for the reason that the resolution is so low that H alpha N2 is completely blended.
But is the O3 to H beta so high that it has to be above the lines?
Look at the second spectrum.
It doesn't
That's a 10 to 1 ratio. That completely, you rule out star formation when O3 to H beta is 10 to 1, regardless of other line ratio. And the second one, the first one I might buy, the second and third one.
No, if you take the H alpha luminosity and turn it into star formation rate, and you take the stellar mass, and you go to the Minucci relation or the FMR, whatever you want to call it, if they were star forming, they would be extremely metal rich. It would be at the bottom of the BPT diagram. If it's a normal galaxy, it would obey the properties that other normal galaxies have. Plus, it's an X-ray source, so at least one of those is an AGN. Which one is it?
The first one.
Why should it be a regular galaxy?
Why should it not be a regular galaxy?
It's an irregular object.
Yeah.
So, I don't know. I mean, when you try to use averages on specific cases, it's always dangerous.
Yeah.
Sure.
And you could get a high X-ray luminosity from star formation. There are...
Again, if you convert the H alpha luminosity to star formation rate, you're off by more than an order of magnitude.
The X-ray is high?
The X-ray is high.
Yeah.
Sorry, but you were telling me that the H alpha was blended with another line. If you were to
with
take
N2.
Away, yeah. So if you were to take away the luminosity from N2,
It's still way too much. Yeah.
Is the X-ray resolved into the clumps, or is it?
No, it's too far off the aim point. We can't associate the individual counts to.
Couldn't the X-ray just be due to one? Yeah.
It could be due to one, but which one is it?
A.
Why?
Because that's the one that's more likely to be an AGN than any of the other letters.
you've crowdsourced it now, so.
Always dangerous. Always dangerous. Well.
The hard X-ray one. I know I asked you this before and I forgot. So is the hard X-ray luminosity?
Oh, I don't know off the top of my head.
For the total X-ray luminosity?
I'd have to look it up.
And how are you getting a mass?
You put down apertures on each clump. Oh, you mean the black hole mass?
Yes.
Okay, that one is really hand wavy, but you put down apertures in each clump. You do the photometry from B through J, H, and you fit various stellar models to get a stellar mass, and then you assume you follow the same relation. Now, so these I would believe less. These are very, very much, this is the best we can do for objects like this. And we try to observe this with OSIRIS, but there's no suitable star nearby, unfortunately.
Any chance of getting better spectra at higher spectrum resolution?
That's what we couldn't do, because there's no nice star. Now, okay, so this one's a pathological case, and if it doesn't convince you, there's another result by another group that basically points in the same direction. So this is by Frédéric Bournon and collaborators, and what they did is they took essentially clumpy galaxies at a lower redshift than my object and said, let's stack them in the X-rays to see what we see. And they were actually careful at one stage to see if they could remove things that had an obvious bulge. And they basically see in the stack a signal. They have a soft, clear detection. They have a very marginal detection in hard X-rays. And if they took a comparison sample of what they called stable disks, they don't get the signal. So these clumpy disks at lower redshift, when stacked, on average, have a signal that looks an awful lot like black hole growth from low-mass black holes hidden in these clumpy disks.
Is there any way to account for that X-ray emission from high-mass X-ray binaries? If you have all this star formation, can you get it that way, or is it too limited?
So it's, well, that's a tough one. What they did is they created this comparison sample, I think, precisely for that point, and they don't get such a
not extreme star forming galaxies.
Well, neither are those disks. These are probably all normal main sequence star forming.
Those clumpy things, those look very star forming.
Are the clumpy and stable matched in star formation rate? No.
I don't know. I'd have to look it up.
Right, there are calibrations.
X-ray luminosity function
Yeah.
of high-mass X-ray binaries correlate to star formation.
Yes.
That's
Well,
the work of the Max Planck. So it depends. If this
Yeah.
is a luminosity of 10 to the 45, there is no way it can be high-mass X-ray binary. If it's 10 to the 40,
X-ray is usually about 30 times O3, so it's going to be about 10 to the 43 in the X-rays if they follow that relation.
right. So it can actually make a strong signal.
Yeah. So I think I think this is an interesting avenue because there's now, I think, multiple lines that point towards AGN or low mass AGN in these kinds of clumpy disk galaxies. And in fact, if you sort of took Hen-Ice to 10, for example, and put it into one of these galaxies, it would be like more or less like one of those clumps. So
How massive are the clumps?
they range widely. I mean, some of them are low mass, some of them can be, I think, 10 to the 7, 10 to the 8, 10 to the 9. So I think this is a really interesting possibility. I mean, we need to work further on this and get better constraints. But I think the idea that maybe low mass black holes keep popping up under other conditions other than just very high redshift, I think should be looked at. And I think in particular, you can always make the case, well, whatever you're seeing is a reactivation of a seed that formed at high redshift. But on the other hand, we looked at high redshift, and at least in the Lyman break galaxies, we don't see anything. So I can go back to the list, and you can come up with your favorite explanation for why we don't see anything. So here's the picture of Hen-Ice to 10. Full glory.
So can you show us where the center is, where Amy's object is?
I can.
Sure.
I can.
Here?
That big bright blob in the middle. Go to
This?
the right a little
So
bit.
between
This?
the two lobes?
Yes, it's right in the middle. Yeah, that's.
I thought it's more like here.
No, it's that bright.
It's here, right?
No.
No, it's here?
To the right.
Over to the right. Keep going.
Here?
Yep. That
Okay.
big blob. That's the X-ray and radio source.
So the two lobes of radio emission that you showed in the maps,
They're
are
on
those the yellow thing on
Yes.
the right and the bright thing
Yeah,
on the
this
left?
is a composite. This was from the press release the Chandra people made. And so there's a 3-color HST image. There's the VLA in yellow, and the Chandra is in purple. So it's all blended together. It's kind of a mess.
It
but-
saturates, unfortunately,
Yeah.
I think, on the screen. So let me make up my conclusions, and we can go back to the list. You can tell me why we don't see anything.
But from the high redshift stacking stuff, you're just saying that there's not black holes that are 10 to the 6.
Well, these are all
Right.
averaged statements because it is a stack.
if
But
it
on the
were
other hand,
significantly lower
if you,
mass back then.
well,
So,
Yep.
yeah, so
Yeah.
a similar question, because in a sense, the mass of the Lyman break galaxies is not really large,
mhm.
and so maybe it's not necessarily a problem if they're not 10 to the 6, larger than 10 to the 6 sort of masses black holes in those
Yeah,
stars.
sure, but so 10 to the 6 at 1% Eddington. So if they're growing at Eddington, we go down to about 10 to the 4. So that's, I think, what makes it such an interesting constraint. And then we go back, well, maybe they're mostly not growing, and then sometimes they grow at whatever super Eddington. Then why don't we see any X-ray sources that could be at high redshift? Like, they have to grow somewhere. And it's hard to hide from Chandra at that redshift.
All your nearby ones were growing at 10 to 100% of anything?
Which ones?
You were saying the one source at
Yeah.
1.5.
I mean, that's really order of magnitude estimate.
Okay.
Yeah.
But certainly not 1%.
Yeah.
There are a tremendous selection of X. In the low redshift universe, the median Eddington ratio is about 10 to the minus 2. In the high redshift universe, it's larger, but that could be all a selection of X.
And even, I mean, it's 10 to minus 2 for AGN.
That's luminosity weighted, not number weighted.
Yeah, but the chances
No,
of just
that's
pick
right.
a galaxy, look at the nucleus, there's probably a black hole, at least luminosity one. The average luminosity is 10 to the minus 9.
Yeah.
So
That's for the ones that
I
are
think
on.
that your, I don't know if it's one, number 2 or 3, the list that you put up at the beginning for why that is that, so I want to turn that in a question for you. Why would you think that your average prime unbreak galaxy selected that way is unlikely to host a highly radiatively dense black hole? I get
this is for completeness. I mean, we basically try to come up with all the explanations for why do we not pick up hard X-ray photons.
So if you went one step further and used models like our Maloney model or Marconi model, where they try to correlate the growth of black holes at all the epochs with the redshift 0 black hole mass function, then they have to come up with strong constraints on the fraction of black holes that are accreting and their Eddington ratios. Have you tried putting these data into that context?
You mean the Eddington ratio distributions?
Well, they have a specific set of parameters which they then Eddington ratio distribution, the fraction that are growing, and they have these boundary conditions based on data, but not your data. And I was wondering if you tried putting your data into their context.
That's an interesting idea, yeah. No, we haven't done that.
I have an observational question. I was warned by a referee not to use that tracer at all.
No, this is a new one.
Oh, okay.
Yeah.
So can you just please, am I the only one who doesn't know what the problem was?
It's a background subtraction. And we thought we had a detection, and it turns out we don't. And you add more objects, you just get a better upper limit.
And so your background subtraction is good?
Yeah.
A question about the Redshift 767 quasars, massive ones, the Sloan quasars. Have they been accreting? Do they have to? We have a problem forming. I still think we have a problem forming. Do they have to accrete continuously since sort of 0, or where 0 was 100 million years after the Big Bang, or 200 million years after the Big Bang, or something? And if so, should we see them all, or see a few of them? There aren't that many of them, of course. But
well, if the black holes in those Lambda break galaxies are sort of growing up at the same pace, we should have seen a booming bright signal. So whatever's happening in what gives us a Redshift 7 quasar is different from what you get in a normal galaxy.
What's known about AGN, like X-ray selected AGN in star-forming galaxies, very active star-forming galaxies? Do we know?
There's a zillion papers. You find your question a little bit.
Well,
what Redshift?
So what I'm really wondering is, if there, why aren't the black holes in these alignment break galaxies? If they are there, why don't we see them? Why isn't the black hole in Hanais 210 growing more? There's all, it's weakly, very weakly accreting, yet there's all this gas around, but there's also all this star formation around. And I'm wondering if somehow the star formation is causing a problem for the black hole growing.
Sure, if you have too many supernovae going off.
Optical and infrared, the answer is yes. Lots of star formation. It becomes much more difficult to find the low luminosity AGN because of obscuration and starlight. With dilution of the lines, pollution of the continuum, lots of dust. In the X-ray band, it's much less so because basically star formation is a much less efficient process of producing X-rays.
Right. So
on the flip side, if you your very dense molecular clouds, then you have to go to very high energies, which at low redshift Chandra can't do. So what's been noted observationally, Sylvain Leduc's work and others, is that if you look at luminous infrared to ultra-luminous infrared galaxies, and you assume that most of the IR is star formation up to a point, then as you go to higher and higher IR luminosities, the fraction of those objects that are AGN starts to increase. And when you're above about 10 to the 11, I think it's the number of solar luminosities, it's approaching more than 50%. And that seems to be true out. Now I'm treading on weaker grounds. I think out to redshifts of twiddle 1-ish. I don't know beyond that if Chandra's sensitive.
So if people have stacked redshift 1 to 2 luminous infrared galaxies from Spitzer and Herschel, I don't know actually if that includes Herschel, but certainly from Spitzer, and you basically do see the hard spectrum and the very fuzzy K-alpha line, indicating that they contain obscured AGN.
Sort of in the border between luminous and ultraluminous.
Yeah.
It's where the AGNs become much more prominent.
Yeah. So, but sort of to turn it around, right? At redshift 6 to 8, Chandra is effectively new star.
Yeah.
So whatever you're picking up should be AGN, and as far as is possible, very little effect from obscuration.
And by answering the implicit question, more general star formation, there are whole conferences on that subject. I think the answer is AGN and star formation are related in some way which we don't understand yet. I don't want to.
No, that's right.
There's all sorts of indications, but nothing locks together well.
Even regardless, even if you have no star formation, they might actually even think supernovae push gas away and make it more difficult for a black hole to breathe. There is this example of the uber-massive like Remco Bang-Bosch black hole, so 10 to the 10 solar masses, 15% of the entire galaxy stellar mass in a black hole. And Andy Fabian had a paper earlier this year because that galaxy turns out to have to sit on top of this multi-megasecond Perseus cluster exposure, and it's close enough that the Chandra PSF resolves the bondy sphere of the black hole. And there's lots of Xray gas within that bondy sphere, and still the Xray luminosity is highly subenergetic. How do you prevent the gas from falling into the black hole and make it brighter?
There's another sort of related interesting observational result from Rick Davies and collaborators, where they took near-infrared IFU observations of some nearby Cepheids, and they found that with very high frequency, there's a very center nuclear region of those Cepheids. That's maybe a biased sample, but that they had more intermediate age stellar populations, no really young stellar populations. And so they speculated, well, maybe it's just really hard for a lot of gas to get down if you have O-star winds and core collapse supernovae going off. And once you sort of age a little bit and your main supply is actually really slow, gentle winds from AGB stars, it's much easier to feed at least sort of a low luminosity Cepheid.
So coming back to something we talked about yesterday, if you believe that accretion occurs always with the same angular momentum vector, if we ever could figure out the spin distribution of black holes, you might be able to figure out their age distribution.
So this is sort of related, and we looked into this a while back, and I think the state of the field is still the same, where people try to correlate the type 1, type 2 distinction of local AGN with the orientation of the disk in which the AGN was sitting. And I think the answer is still that there's no correlation. So at least those low-mass, local low-luminosity AGN are fed with something whose angular momentum is not set by the large-scale angular momentum of the host galaxy. So maybe it just gets scrambled that way.
We know that those have grown so significantly that they should have adopted whatever the angular momentum is of the thing who's currently feeding them.
Who knows?
say anything about the Xray background at these high redshifts? What contributes to it?
That's a very interesting question. There's a recent paper in the last year or so about the X-ray background and how, I'm not going to remember all the details, but they basically thought that blue, low-mass galaxies actually contributed a significant amount of the hard X-ray background. Xray paper, does anyone know what I'm talking about?
Yeah, basically they took out all the point sources and they they stacked on all the optical, basically almost all the optical images, and they got a net signal which would reproduce the missing quote-unquote flux. And of course, I don't know what it is that does it, except it's related to optical light.
Yeah.
But they did the sources. They looked at.
Oh, by type?
Yeah, the mass. I think it was masses and colors and various things, and they generally.
What's his name?
I saw that.
Does new star places any new constraints?
Not yet.
Not yet.
That's the radio astronomer. It's the X-ray astronomer.
TriStar?
No. It used to be a Columbia.
Oh, Christian Size.
No, not Christian.
Oh, yes, Franz Bauer.
That's it. It's Franz. I think it's Franz Bauer's. Well, he's at least one of the authors.
It's right back there.
Now, New Star has not yet gotten enough observations to comment on the X-ray background. But we have it back, actually. We have a paper that's just been published. If you want to take a look at it.
Does this constrain anything? I mean, can you constrain using the X-ray background? Constrain any of these?
You know, all we notice is that if you basically add up the whole low redshift universe, its X-ray spectrum looks just like the X-ray background.
Yeah.
There was a paper, I'm looking this up because I didn't remember any detail. This paper, Salvaterra, Hard Voluntary Molecular Steer, they're using, I think it's the unresolved X-ray background when it's measured by Swift.
Yes, I remember that paper.
As the same place, we place firm upper limits on the global accretion history of massive black holes with redshift higher than 5 from the recently measured refraction of the cosmic X-ray background. Maximum allowed unresolved intensity implies a maximum accreted mass density of a certain number. So this basically favors black holes are rare in high redshift galaxies, so their accretion is efficient only for black holes hosted by rare galaxies.
Yeah, so the luminosity is compared with that.
Exactly.
Well, the one caveat in that always is the individual sources, right? You know, do we miss by the Lyman break selection? Do we miss the ones that are actually growing? And I think the answer is starting to point into no, with the caveat on that being X-ray sources that have no counterpart.
Oh, I guess this was saying that the background is a global constraint.
Yeah, I mean, there's always, you can always fudge with the background a little bit. I mean, the sources that dominate the background are moderate redshift.
Yeah, Kevin,
Yeah.
did you try taking the observed evolution of the AGN luminosity function and extrapolating it to your redshift 6
Yes.
8, and these points are consistent, inconsistent?
I'm trying to go off memory here. I think if you take the Hopkins bolometric luminosity function, you're sort of okay. If you take Willott and if you take Ueda, I think you have a problem. But I have to check the figure.
Now I'm going to show my age. Not just graduate student, postdoc. The guy did his PhD thesis on another model of the X-ray background. I'll show you.
Okay.
Anyhow, but it's not wildly inconsistent anyhow.
Yeah.
So it's just that the whole AGN phenomenon is dying off as you go to higher and higher redshifts. And at these, as best you can tell, it's not there.
Yeah.
You don't require discontinuity in the evolution.
So, but okay, so let's take this as let's assume this is right, and sort of most high redshift galaxies either don't have black holes or they're not growing. How do we constrain seed formation? Like this is the issue where I get to. If the theorists say we need zero metallicity gas to make seed black holes, they should be around, but they're not. We don't see them.
Or is it telling you maybe that you have some kind of short redshift in the density or mass of the galaxies that can actually form the black holes by direct collapse, for example.
So you're saying direct collapse happens at redshift 4 or 5?
Yeah, but only only above a very high circular velocity scale. Above, the very high sigma peaks. You have to be 3-4 sigma peak. Direct collapse or not? What do you do now?
But then how do you explain the low mass black holes today?
Well, you probably need two modes, but a high ratio you might have that dominant,
right,
and then a second mode that picks up later on.
So basically you make the redshift 7 quasar, the black hole, you make that at redshift 20, and then you make the low mass black holes at redshift 5?
For example. Yeah.
But then you have to be really good. Well, if that still requires essentially zero metallicity, you have to have a ton of halos.
No. In fact, I don't think that zero metallicity is.
Okay. So what would be the signature of that happening at redshift 5? What should we be looking for? Like, could you make a prediction on what the Xray luminosity function would look like, or space density, or anything? Because I think we're on the edge of being able to make that kind of measurement. You should do the maybe you can do it in your head. Would we have if Henai's 210 was the average Lyman break galaxy at redshift 6? Would we have gotten a signal? I think the answer is you're marginal. No.
The Xray?
Yeah.
No.
How faint is it?
The Xray is 5 times 10 to 39.
Oh, okay.
And yeah, just that source.
Right.
It's not a quasar. Any hard X-rays.
That's just the hard X-rays.
No, but it means if you put that at redshift 8, then you see that their rest frame is much lower than ours. Yeah.
Okay, so we have a mystery.
So, do you doubt that 4 is the answer?
I was hopeful about 4. Now that we've had a closer look, I'm less hopeful about 4. Ultimately, if they're growing by accretion and there's not something really odd going on, they should be X-ray sources. And so I think the only place for them to be left hiding are X-ray sources that don't have an optical or near-infrared counterpart at all at incredible depths. So my take-home message is that the space is getting tight for you. You don't have complete freedom anymore for your favorite formation mechanism. There are now constraints that push you.
Okay, so we have the quasar, this is high redshift, right?
Mm-hmm.
And so these are, and we see those very massive black holes.
Mm-hmm.
You were looking at the very low mass ones.
Well, what do you mean by low mass? They're low mass galaxies right now, but they're not. They're still high sigma peaks.
Oh, okay. We have very massive black holes.
Yeah.
Maybe don't have the low mass ones. What do we have in the middle?
Right now we have nothing because we don't have a larger area deep X-ray survey. So the closest thing we'll get is the square degree or so from Cosmos. So that's the next step.
What I would say, okay, maybe you just form them at 10 to the 6, 10 to 7 actually, relatively massive black holes, and then they don't accrete until relatively late. So you won't see the very low mass ones.
Do we have a viable mechanism to make 10 to the 6, 10 to the 7 with regularity?
10 to the 9, so I think that should be easy.
What if they just grow really fast? You make something like it grows very quickly and is big in your 10 to the 7 regime and quiescent in space. There are no more things being made. You just leapfrog right over the boundary.
Well, okay, so growing really rapidly, growing super Eddington or whatever, as long as it still emits photons, as you would expect, where are they?
Well, they're not doing anything at redshift 6 to 8. They did it at redshift 12.
Okay.
So it's like an inflation.
Yeah, they're ravenous and bulk up.
But only right then, because then whatever mechanism does that can't operate anymore, because then later on we get.
And so not only that, so they have to completely stop, because if they're 10 to the 7, they basically have to all be not accreting on average. Yeah. And yet they sit in Gasrich galaxies.
But again, we have 10 to 9.
Yeah.
Certainly, you can make these things.
Absolutely, you can make
much
it.
easier to cut it off before they get to 10 to 9. So maybe we have a reverse bound. We can form very easily.
Yeah, and something. So what stops them? Right? If you're in compact gas-rich galaxy, you're bound to run into a cloud of gas, and accrete it.
Well, isn't it even a problem in lower redshift galaxies, just getting the gas down into the center? You have lots of certain nuclear star formations, but they keep getting the gas into the center.
Right.
It's like work by So maybe it's just a universal.
Okay. But so that still leaves. So maybe that's true, but that still leaves you the problem that. I guess it's not too visible too well on this plot, but these are sort of from the Xray luminosity function, these gray points here. So by redshift 3, 4, 5, we see a lot more accreted black hole mass density in the universe. So what we're basically saying is that the universe does this, you're down here, and then you jump up here, just past the point where, yeah.
Well, we do see a strong increase in number of quasars at a redshift of 4.
Mm-hmm.
So
it's a continuity.
Yeah.
It's rising rapidly from 6 to 2 and then flattening.
Yeah.
There's also a missing dimension here, and we should be careful because the redshift 7 quasars and even the high mass quasars at lower redshifts, right? One doesn't translate necessarily directly in the other. Redshift 3, 4, 5 to the 9 and to the 10 solar mass quasars are still very rare objects.
Kevin, at 06, do these have Lyman alpha lines?
The Lyman break galaxies?
Yeah, that's right.
I guess so. The redshift 6 ones, the ones that people have observed, mostly show Lyman alpha, I believe.
So, in particular, this sample that is being used to constrain the Xray.
This is photometrically selected samples.
So
Yeah.
you would not know, right?
Yeah. Most of them are too faint to take spectra, we worried about that. What if the sample is actually highly impure? But okay, so let's make worst case scenario. Let's say half the objects in these samples are low redshift interlopers or whatever, right? Okay, you move the constraint a little bit up here, but you're still in uncomfortable territory. Like the constraint doesn't go away even if you say 50% of the sample is contamination.
Just to say again what I said a little bit earlier, well, we haven't done the numbers correctly. It looks like this upper limit is simply a continuity of rapidly declining quasar population at high redshift.
Okay.
So in other words, it's an extension to even higher redshift to what's been seen at redshift 5, 6 already.
Right.
So it's saying that whatever process this is, it's not a new process that's turning things off at redshift 8.
Mm-hmm.
It's a continuation of the same process.
So that will point towards a scenario where most black holes either don't grow or form actually much later than redshift 20 and then rapidly come up.
Yeah. Right. So either they're being created or growing.
Yeah.
Okay, but then there is also this option, I think it was 3 out of the 4 choices, the obscuration. There's two different forms of obscuration that I can think of. One of them is that there is this really intense starburst cooking dust in a very small volume of space that also contains a growing black hole.
Mm-hmm.
Another possibility is that the accretion flow itself is launching this wind that is absorbing the X-rays.
Yes.
And maybe most of the energy is coming out in this hydrodynamic outflow, not a radio jet, but a hydrodynamic outflow, which then is going to come to a stop somewhere when it encounters the ambient ISM. It's kind of like a supernova that's always remnant that's always on. It's like it keeps. So
would it be fair to put that in the quote unquote radiatively inefficient box general class of explanation?
Based on inefficiency,
I mean, it's not the same thing, but it's in the same direction.
It's relatively inefficient in the wavebands in the X-rays. But eventually, this energy will get reprocessed either into nebula lines or into the infrared if it's far infrared if it's dust.
So we need to wait for JWST to see that.
Yeah. Maybe. Well.
But so in this picture, would you absorb even the rest frame 20 keV light?
I don't know. Of course, this is not really a precise model.
Yeah.
Just.
I mean, of course, we worry about obscuration. I mean, I list it as one of the explanations, but of course, again, at Redshift 6, you're really looking at the very hot X-rays.
So this is sort of an observational question. So in the low redshift AGN, when you're close to the limit, the outflow from the object is very strong. Do we actually at some point start losing the X-rays?
It's not the picture is not the geometry is not isotropic. So that's the suspicion.
And I'm not talking about geometric effects, but more so of the theorist fantasy here.
Are you thinking of like a GTK type effect?
Well, sort of this, again, theorist fantasy, imagine that the disk wind is so strong that you are not going to have this non-thermal coronal population to produce the X-rays. Instead, it's just going to be, thermal outflow all the way out.
Well, the observational object you may be describing is called the BAL quasar, where we know there's a very strong wind. You see these enormous absorption features. And BAL quasars are indeed X-ray weak. And now, we're not exactly sure why. 2/3 of the people believe it's due to photologic absorption. 1/3 believe it's some more process more like what you're describing. So let's leave it at that.
BAL quasars are also typically very dusty.
And Lyman break galaxies are not.
Dustiness in quasars is actually really expected theoretically because the same flow that's feeding matter to the quasar will also be forming stars. And these stars are going to be, of course, reaching the end of stellar evolution, exploding supernovae in a very dense environment where the supernova remnant will never have chance to, people will thermalize. It will radiate out on a time scale of 10 to 100 years. And it's possible that even that you may even have dust nucleation in the gas phase very early on. So just dust in AGN is to me a natural outcome of the fueling.
But the strange thing about the BALs, if they're dusty, you still see UV light. It requires very strange geometry / photoionization to see UV light and block the X-rays.
But
you can do it, but it's...
Do you have a way of telling whether this UV light is atmospheric, as it's in a disk atmosphere, or whether it could be just purely nebular UV light?
Nebular is in
combination.
Nebula is in combination lines in
it doesn't look like a combination because it's a big blue zone.
So I should add something about
like that of a combination.
So there's been a lot of controversy about how to do the BAL stuff. It's not so easy to understand.
And is there for BAL, is there a sort of minimum black hole mass or something that?
No, you can't get the mass.
There's no mass indicator left at that stage. With that weird spectrum. Well, maybe the Balmer line. No, the Balmer line.
10 to 15% of all quasars are BALs.
Yes, but if they're high redshift, it's kind of hard to say.
Yeah, that's right.
Absorption is not coronal.
But I don't know if anyone's actually gone out to check infrared
spectrum.
But there are.
That's right. Yes.
So you have to find BALs that are.
So I agree. I mean, if you want obscuration to be if you want obscuration to be your explanation, you need to do something beyond what we see in normal AGN, and there's a geometric point here, which is that we're looking at a stack, so they better be heavily obscured 4 pi.
Well-known
Yeah, we include it for completeness' sake, but I don't like obscuration.
Even the once you go in the non-star band.
If it was something, if it was like a kind of spectrum, say like NGC 1068, I mean, again, you pick it up.
You would.
Yeah. So.
What was the comment number 3 about growing by mergers? How does that save you?
Well, mergers don't emit photons, at least not as accretion would. Yeah.
On the way you.
Yeah, there should be.
On the way you bring a lot of gas, maybe.
Yeah.
Yeah, but it's not that the merging galaxies would not be selected by your alignment.
No, I mean, there's no reason to think that.
Plus the mergers give you a low growth rate. You can only double the mass.
You can only double the mass, so you have to have many mergers in a short amount of time. So I don't like mergers for that reason, but again, we have to include everything at this stage. Yeah.
Is it still true that it grows and the high redshift is dominated by mergers and kind of transitioning more towards accretions?
Should ask the theorists.
So somebody made the comment, if you have, maybe it was, let's say you have.
If you start with a couple mergers, you get a head start.
Yeah.
If you start with a number of mergers, you grow the mass by an order of magnitude, then is that good enough? Give you unlimited growth?
Yes, I think it can be.
But again, I mean, okay, let's assume that mergers are dominant. In between the mergers, they must not start to accrete, at least to some degree, because otherwise, again, we would pick them up while they're accreting.
Well, but if they accrete,
But the point is,
maybe that's the way. Enough
to
factors.
be efficient, the mergers need gas. So why would they not accrete every time that they merge?
Yeah. But what if they accrete every time they merge? But these mergers are dusty galaxies early on. So.
But again, we look at rest frame hard X-rays, so.
Well, what if it's okay if they don't accrete? We were just saying that. And I
Yeah.
is always gas, it doesn't accrete. The Milky Way is always gas, it doesn't accrete. Like sometimes
No,
it's okay.
no. But if you sure, the Milky Way right now doesn't accrete, but if you take Milky Way-like galaxies and ask what is the average accretion rate, Milky Way-like spiral galaxies actually the galaxy most likely to accrete in the local universe.
The what? What was the last bit you said?
Milky Way-like galaxies. So if you ask what is the average Seyfert galaxy look like, and Rich is like, the X-ray people knew this 20, 30 years ago, the Sloan people were led astray for a while. I can tell the whole sociology of that. But the average Seyfert galaxy in the local universe is a massive disk galaxy.
But the average disk galaxy is not a Seyfert.
You're right.
That's true.
10%.
Yeah.
If you,
Right,
what is the fraction of this
But
galaxy that
in
are
a
secret?
redshift
That's the
of
point.
1, that's not correct. In a redshift of 1, the average Milky Way galaxy is a secret.
Okay, so that which is what you expect.
Right.
More gas.
I thought
Well, it's 1
10%.
plus z to the 4th, so 2 to the 4th is 16. We know it's z of 1, and z of 0 is 10%, so 16 times 10% is 100%.
Yeah. Well, again, to
Well,
the
then it can go by no.
No, but it's actually, no, it's true. As
So-
you go up, as you go to higher and higher redshifts, the fraction of massive galaxies that are AGN
Yep.
gets to be very large. I'm not saying it's 100%, but it's a large number.
Yeah.
Larger.
Large. No, I think it's actually large, at like 50% for massive galaxies.
They have to be.
Massive.
Massive means Milky Way like.
So yeah, I hope what I'm conveying here is that we're now entering the regime where we can say things, and if we'd gone just by the naive predictions from, let's imagine 1 or 2 of these seed formation scenarios were true, we would have naively expected to pick up something, anything, and at the moment at least we have no trace of black hole growth in any galaxy of any black hole except for the utterly exceptional quasar. So we need one or more explanations, and so I think this is really the starting point of trying to figure out what's happening. And I still like black holes being formed at late times.
So okay, could you go over, because we're sitting here getting a little confused, maybe it's because we forgot what the real argument was. So you said about why KITP below the detection limit, because I mean, if you actually have something that's really heavily obscured for that matter, or just smaller,
Well, so just for the numbers.
This is really early, redshift 6 or 8 for not limit galaxies.
The universe is a couple of 100 million years old.
Yeah, but they're really, really numerous around redshift 3. This is really early.
What is really numerous?
The limit breakdown.
Well, as far as we know, obviously this subject to revision once JWST is up, as far as we know, every galaxy at redshift 6+ is an Lyman break galaxy. Nobody has yet discovered like dusty or passive galaxies at that redshift. Well, yes. Which is why we turned it around and said, what if the Lyman break selection misses all the galaxies where the black holes are growing? And we certainly, at least so now, we haven't found any.
I would like to direct everyone's attention to what Richard
Okay. What he's eating, you mean?
agrees with theory.
Okay, thank you. Thank you very much.